Okay, let's start from. Oh, I think I made the number 7.2. The rules on integration. Ah, okay. So far, last time we defined the integration for single and two variables, and also three variables. Now we're going to talk about how to compute such integral. So remember that when you take the integral of two variables, finding the volume, of course, that's when the function is lying above xy plane. If it's below the xy plane, it's the minus of the volume. But let's take this geometric picture for a while so that you can get the idea of what. So how do we get the volume under the graph of over this two-dimensional rectangular region? So one way doing that is you cut this volume into thin slices of smaller volumes, and then sum them all the way up to from the left limit to the right limit. So let's say I take the slice at x, meaning that I take a plane perpendicular to x-axis at x position. Then I take the slice. There is a section of this volume, and I call the area of this section to be AX. So I'm assuming that I'm doing for every partitioning point of my X range. Let's say we have n partitions of the range of X, then it means that I get n slices, thin slice of this volume. And I know that the area of this slice is A of X. Then all I need to approximate the volume of the slice is assuming that the slice is some sort of a cylindrical slice, thin, very short cylindrical slice, so that it has a flat side on the boundary. So that if I take the area and multiply it with the width of the thin slice, I get the volume. So it's like, again, this AX I star times delta X is not exactly the volume of the slice, but you're approximating the volume by this thin rectangular straight up slice. So the question is, how do we get the area AX? So how do we get the area is when you're looking at the area AX, and let me go back to the slide here, you can rotate the plane that you cut the volume, and put it into XY plane in some sense. And then, or you can say that it's a YZ plane in this case. So this is the x-axis, z-axis, and z-axis, y-axis, and z-axis. So you look at the slice of the volume in YZ plane. You can calculate the area by integrating the region as if it's the region under the graph of the function over the right y range. Okay? So what you want to do to find a of x is the integration of the function over the range of y from c to d, because the y range is d. But here, the catch is you're assuming that you fix the point x. Okay? So when you're integrating to get the area, you're not changing the x. You're assuming x is constant. So you're looking at the function as if it's a single variable function of y only. So this means the z coordinate, which is the height of the rectangle, and dy is the width of the rectangle that approximate the area AX. So then you can do the same thing with the A of x to get the volume, integrating the a of x, the area times the small width and over the range of x from a to b to get the volume. So you can get the volume with the definition of the double integral, which is by taking the lattice partition of the rectangular region D, and then for each small rectangular region, you take the height of the function and then multiply the area of the small rectangle to the height to get the volume and then sum them up. That's the definition of the integral of two variable function on the left. But you can do the same thing because what you're trying to get is the volume. You can do the same thing in a different approach like this. So these are not the same thing. So the claim is we are not defining integral as this integral. It's a theorem. Theorem says we have a notion of computing this integral, and we also have a notion of computing this integral. But this is simply doing the integration twice. So doing the single variable integration twice. So it's called an iterated integral, and this is just integral, or sometimes called a double integral. Theorem says that if you can, if your domain is the rectangular domain, you can calculate the double integral by iterating integral of the same function. And it doesn't happen all the time. So there's one condition, it's a strong condition, but it happens when f is continuous all over that rectangular domain D. Okay, so that's our Fubini theorem, and let's see an example. So here we have some kind of a saddle surface. So we have a up and down over the rectangular region. So this is our function, 1 minus cosine x sine y. I want to find the area, volume under the graph. Okay, so as I said, you can compute the volume by dividing or partitioning this entire region into n square number of subregions. But let's use the Fubini theorem. So I'm going to do it for you, and then I'll let you do the other examples. So here, okay, so 1 minus cosine x sine y dx dy. So before you apply Fubini theorem, you need to check whether it's continuous. But cosine and sine are continuous functions. Of course, it's continuous. So I want to apply the Fubini theorem. Let me get the right x range for 0 to pi, and y range for minus pi over 2 to pi over 2, and cosine x sine y. So now, when you write iterated integral, so in the double integral notation, dx dy is just symbolic notation. Doesn't matter whether you write it in dy dx or dx dy. But when you write iterated integral, you need to specify which variable you take integral first. So when you write the iterated integral this order, minus pi over 2 to pi over 2 is the range of the variable y, not x. So you are taking the integral over y first and then x. So in some sense, in the statement of the Fubini theorem, I put the bracket like this here, but usually we drop the bracket because the order of integration is specified in the order of dx and dy here. So we don't really need to put the bracket all the time. So we just drop the bracket. And let's do it one by one. So in the first iterated integral, you have to start from the inside, not outside. So I'm taking integral over y, assuming x is constant. So it's similar to the partial differentials. Partial differential, you take the differential of a function as if it's a single variable function, taking all other rest of the variable as a constant. So here I take x as a constant and consider y is only the variable. So the integration over 1 is y, and then cosine is constant. And what's the integration of sine? Minus cosine y. So that's from minus. So since it's confusing if I just put the limits, whether I should put the limit to x or y, so it's better to specify the variable that I'm going to put the limits here, and then dx. So before carrying out another integral, let's make it simpler. 0 to pi of pi minus cosine x. And what's minus cosine pi over 2? Oh, it's 0, right? Is it right? Yeah, y range is 0. Yeah, so it's 0. Dx. Right, yeah. And here, minus y, okay. So what's the integration? Simply integral over 0 to pi of pi dx, which is pi squared. Okay. Okay, so let's talk about other type of domain. If we have non-rectangular shape domain, how do we use the Fubini theorem to find out volume? So the ideas are the same. So we're taking the section of this volume and then let's say if I take the section perpendicular to x-axis, then the area is parameterized by the value of x. I'll call it ax. I'm taking the small volume of each slices. So when I have a domain given as this one, so my x is ranging from a to b, but my y is not always range from constant. So there are certain boundaries that restricts the range of y. So like this one, so when x, so this is the x-axis, when x is changing, the range of y that you can put into the point lies in the domain is restricted by the graph, this one and these graphs. So you can imagine that these lines are graph of two functions, g1 and g2, and this is our definition of domain. And how would you find the area? The area is also just integration of the curve that bounds the height here, and the range of the integration to get the area, section area, is the limit of y, the range of y. But range of y is bounded by these two numbers, g1 and g2. So you put that in here. It's okay, it's not a function because we're assuming that x is considered as constant. So you're taking an integration over a constant of this single variable function. And then once you get the formula of ax, then you take the integration again to get the volume. So you can do the similar thing. You can do the exactly same thing with opposite direction. So suppose you take a section perpendicular to y direction. Now, even though I put the same symbol ax, it's different side, different slices. But ideas are the same. You're changing your y, say from C to D, and at each y you get range of x bounded by graph of two functions. One is h1, the lower limit is h1, and the upper limit is h2. You want to integrate over these range h1y to h2y to get the area ax. So you get this formula. So the difference is that you change, you have different order of integration. So in this case, it's dx dy, but in the previous equation, you can see that it's dy dx, dy dx. So I'll give you an example here. Let's try to find the integral. So before you just not before trying to find this by Twilly theorem, first try to write down the equation or write down the formula of iterated integral that has the same value as this one in two different ways. One by integrating x first, and the other integrating by y first. So try this, and then I'll walk around if you have trouble. If anyone have question, raise your hand so that I can explain more. So take your piece of papers if you need to discuss. 펜도 가져왔대. 가위가 없지. 이렇게. Okay. So these pictures are actually the same picture of the example. So what's the domain? The domain says when x is range from 0 to 1, y is range from x, not 1. Okay. So y range is depend on x, value of x. So when you fix x, you want to find this area, A, the section of the volume perpendicular to x-axis. So how do you find this area? You have to integrate over the y range from 0 to x. So after you get the ax, you take that, so this entire thing is ax, integrate over the x. So the first way of writing the writing the integration will be so the inside doesn't matter now. So all we are doing here is just writing this integral over as an iterated integral. So xy so I'm gonna write it in this way. So I'm going to integrate the area over the x-axis. That's my volume. So what's the area? I have to integrate from 0 to x of my function over y. That's the first way of doing the integration. Now, let's do it opposite way. Let me show you the picture again. Here, the second picture is taking the slice in the opposite direction. So in this case, your y is moving from 0 to 1. But x is now bounded from where? So when y is fixed, what's the lowest value of x? When you cut the slice, get the section. Let's say look at this line. So you have the x coordinates lying on this point. So what's the minimum x here? This line. What's the minimum value of x? When you cut the volume at the y, this is y here, you cut the volume perpendicular to y at y. Where is this intersection here? What's the x coordinate of this intersection? Y. So you start your limit of x from y, and what's the upper limit? How far you can move? What's the value here of x? 1. So always 1. You can always move up to 1. But depending on where you cut the volume, the lower limit is changing. So you want to integrate from y to 1 to get this ax. So you can change the order of integration by changing the definition of your domain, but the same domain. When y is from 0 to 1, x is from y to 1. Okay? So with this perspective, you can write the same definite integral from 0 to 1, that's for y, but for the area, you have to integrate over x, because ax, the section, is lying on xz plane, from y to 1 of the function. Okay. So you cannot simply interchange this. It doesn't make sense, because if you just put the 0x on top, on the outside, your result will have x in the formula. You don't get the number. What does that mean? And simply it doesn't make sense, and it doesn't give you any number, any answers here. So you have to change. So you have to think about the geometric picture. Okay. So whenever you try to interchange this order of iterated integral. So raise your hand if you have any question. So I'm not sure whether we have more example, but let's see if I have one. Okay, so maybe we can work on this example after. So let's look at three-variable function. Let's look at the integral of three-variable function. Now, we can have the rectangular region, cubic region, but let me generalize for the. Suppose that my region is defined as follows. So the same idea, just making it a higher dimension. My region, all the points in my region has x coordinate range from A to B. And at each x, if I cut the section of that volume, y is only ranging from g of x to g2 of x. Okay, so depending on where I cut the volume, I have certain range of y that contains the points inside the volume. And also, when I fix that y, that means I cut that section again to get the line, z-axis, the range of that value on the z-axis range only through h1xy to h2xy. So you can imagine that this is the volume hovering on xy plane, and when you project that volume onto the xy plane, the orthogonal projection, you get some area, the area D. So these two conditions explains how the area is defined. Let me draw the picture, since I didn't put the picture here. The general picture is, let's say we have some volume on three-dimensional space. So when you project it, let's say this is my D, this is R. So R is defined to be A x, b, and so on. Now, when you project your area, two-dimensional area, is defined to be this way. Okay, just taking the first two inequality condition. That's your D. And what we are doing here is when you try to get the integration over R, that means every point. So every point. Did I change the screen just now? Did you see this? Did you see this one? Did you see this screen? Okay, so when you take the integration over R, you're taking a partition of R, or maybe you can partition the big cube that contains R to get the integration. Anyway, you take the partition, and then for each partition, you get the volume of small region, and then multiply to the function, three-variable function, and sum them up. But instead of doing that, what you can do is taking the slice of the region under it, region D, and then on top of these slices of D, there are long cubic region on R, which approximate the region R. So you take that volume and then multiply it, you're not multiplying it, and then you take the integration over that long volume. That's what we are doing here. So let me give you an example here, the more concrete picture. So let's think about what we are doing. We have the region R defined by three sets of equation inequalities, range from 0 to 1, y range from 0 to 1. That means our projection of this volume is a rectangle bound by x, 0 and 1. So you can see that it's a rectangle, but that which determines the height of the volume is bounded by, well, lower limit is constant, but upper limit is x squared. So when you pick one point in the region D, x, y, the height only depends on x, not depend on y. So when you go vertically in y direction, the height is not changed. Have a flat surface, but when you move x direction, then height is changing. So it's getting higher, higher, higher. And the height is following x squared function. I want to integrate this function, x, y, z, three-variable function, over the region R. How do I do that? So you cut the section. Or how do you cut the section? Okay, let's follow this order. First, I cut the section of the volume perpendicular to x-axis. So, okay, so this picture is trying to get the section of the volume perpendicular to z first, but well, let's do this one. Okay, so this picture is. Let's follow the picture first, and then I'll do the other direction. So let's cut the section perpendicular to z. So when you cut the section, you always get the rectangle. Right? So the rectangle has the limit of x and y, the range of x and y, and they are independent because it's a rectangle. What's the lower limit of x? When you cut the volume at the height set, what's the minimum value of x that lies on that section? Z? Root z, yes, square root of z. And what's the maximum? 1. And what's the minimum of y? 0 and 1. So you want to find out the area of the section and then multiply it to the thickness, the width of the slice. And then what you want is, actually you have to multiply. We have to multiply this function value. Let's try to compute this in this order. So integration over R of x, y, z, dx, dy, dz. Again, when you write this just as an integral, in this case it's called a triple integral, it doesn't matter whether you write dx, dy, that's change the order. It's just a symbolic expression. But when you try to get the iterated integral, you have to be careful. So let's see. This is the z range. We cut the section perpendicular to z first. So that's why we put the integration of z at the outermost integration. And then y range from 0 to 1, and x range from root z to 1. Okay, so that's our domain. That's our domain of integration. And when we get this, we get a small portion. So we get function x and y and x, y, z multiplied, so that we get integration all over dx. Then after we done that, we get the integration over dy and then dz. So the integration not hard, but let's do it opposite direction. So not changing by changing the order. So this is y range and this is x range. So instead of taking the dz at the end, let's take these x at the end. So what I mean by end is the last integration. So I'm gonna do dx integration and then let's see, dy integration and dz integration. So I need to determine the limit of these three integrations. So how do you find the limit? So you have to look at the picture again. So look at the picture. Suppose you cut this volume in x direction, perpendicular to x direction. So you still get the rectangle, the mean that you cut. So then you get a rectangle lying on y direction. So what's the range of y? When you cut this volume perpendicular to x-axis, what's the range of y of that section? What is it? 0 to 1, yes. So you get. So by the way, so what's the range of x? X can be moved from 0 to 1, but when you cut perpendicular to x, y still range from 0 to 1. But now what you're doing is, in the section of this volume perpendicular to y, you cut that section again perpendicular to y. And then you get the line, right? You have a double section, you get the line. And line is some portion of this volume ranging from a certain number to a certain number. So what's the minimum value of z in that double intersection? What's the minimum? What's the minimum value of z? Yes. 0. And what's the maximum? X squared, right? It's right here. So your range, your domain of integral is 0 to x squared. So you now can change the order of iterated integral. You can see that these limits are now changing. Okay. So what's the rule? There's no rule. You have to look at the geometric picture. You have to somehow visualize your domain and then translate it into the range. So that's how I do it. Sometimes in the old days, I've seen some students are doing purely arithmetically changing the representation of this range or the region. And I don't know how they do it, but they somehow probably have a picture, visual 3D picture in their mind to do this. But I rather like to draw the picture and see how the section look like this one. And that's how I change the representation of the domain. Okay, so well, as long as you can do it, the integration technique is not that hard. I mean, it's not that important because just getting the numbers, and I don't want to get into the technical detail of this, but you have to understand that this Fubini theorem is when you change the order of an iterated integral, it's not simply changing the integral symbols. Okay, that's all you need to remember. When you change the order of iterated integral to get the integral, triple or double integral, don't try to simply change the order. Okay, that's all you need to remember. All right, any questions before we move on? Okay, so there are one more thing that I want to emphasize. So far we talked about integration by iterated integral, and the other is integration by substitution. So this one is similar to the integration by substitution of single variable function, but we're talking about the double and triple integral. So what is it? So let me just state this first and then explain what that means. When you have the function which transform the domain, yeah, so I wrote this way. So transform the domain D to R. So I'm assuming it's two-dimensional region. So D is lying in XY plane, R is lying in UV plane. So you can imagine this transformation T is sending point X, Y to U, V. Call this Jacobian. This is just a symbolic notation for Jacobian. People write some literature say it's J sub T, something like that. But I like this expression. I'll explain why. And this is simply the determinant of differential. You can see that this is 2 by 2 matrix whose entries are partial differentials. And this is exactly the differential of the two variable function t. But the Jacobian is the determinant of the differential, not the differential itself. That's the difference. And what does the integration by substitution say? You're simply changing your integrating domain. So on the left and right, the difference is that you have D on the left hand side and R on the right hand side, integrating domain. And you also change the integrating variable, dx dy, because D is xy plane, and on the right, du dv, because R is in the uv plane. But I want to make it the same. So suppose that I have simply a function in u and v. I want to rewrite my integration to get the same value in terms of x and y, integrating of x and y variables. Then what I need to do is make this function in terms of x and y by taking the composition with the transformation function t. And then that's not all. We need to multiply the absolute value of Jacobian to make it same. So that's the catch. So you can simply change your function in terms of uv to in terms of xy by substituting t, because t is a one-to-one correspondence. Anytime you pick a u, v, you can identify unique point x, y that corresponds that. So it doesn't matter whether you pick uv to compute f or xy to compute f, because you can send xy to uv and then compute f. So these two functions are the same function, simply changing the perspective of how you get the value. But just changing the variable, changing the expression is not enough to make the same integral. You need to multiply some factor to make it same. So what does that factor do? Let me give a picture here. So there's a idea you can read later. So it's a small letter, but anyway. So what does the transformation do is, let's say this is, okay, so it's different notation here, but let's assume that this is D, and yeah, so change this. So, okay, so I said that it's xy to uv plane, but here I changed the notation here, so maybe you get confused here. So assuming that this is uv, this is xy, left hand side is xy, and right hand side is uv plane, and this is your domain D, and this is your domain R. Just let's stick to our notation here. So stick to our notation. So T is from D to R. D is the xy plane. R is uv plane. Okay. And look at this picture. What I do is I actually want to compute the integral over the region R here, which is in the uv plane. That's my goal. But I want to translate that integral as an integral over the region D. Okay, so that's in xy plane. So how do I do that? Suppose that I subdivided my region D in xy plane into lattice regions. Then I can this transformation, and this is not f, this is t, is one-to-one correspondence, so that each subregions are mapped into each of these partitions, because I can map these read lines by one-to-one fashion to make the partition of my region R, and then you can see that I made a color here, so each blocks are mapped in smaller blocks in the region R. Of course, this is not rectangular partition, but it's still partition, separating into smaller pieces. And let's take a magnifying picture of these colored blocks. Okay, so when I magnify this, what I see is it's a rectangle of width, the horizontal width is delta x. Sorry, so it's not u, it's different. So it's delta x to the horizontal direction and delta y in the vertical direction, because delta x, delta y are the length of partitions. And simply the area of this small part is delta x times delta y. Okay. So how about the area of this part? Now, look at this region. This is not a rectangular region, nor is it parallelogram, but we can approximate these somehow curved region, whatever, and similar to parallelogram, bounded by two vectors, this one and that one. Okay, so where does these two vectors come from? It comes from the vector bounding the rectangle on the uv plane, the xy plane, the domain D. So when you try to get this region, you can simply take the four corners here, but also you can take the left bottom corner, the smallest value here, and then move this point horizontally by delta x amount and vertically by delta y to get this bounding vectors. So in some sense, you're taking a vector, the standard vector E1 multiplied to delta x, and standard vector E2 multiplied by delta y. So these two vectors are transformed from these two vectors by the differential of the transformation function. Because what the transformation function do is simply taking one point to another, and what the differential of transformation do is translating the movement of the point from the domain space to the codomain space. So when I move my point in UV plane along this direction with certain amount, then I get certain movement in the codomain space, and that movement is the vector represented here. So what is this V1 and V2 vector? If I don't have a slide in here, then I'll write it here. So what's the movement? Let me write it here. So I said dt is sending a point, the movement of the point UV to E1 direction delta, sorry, not UV, so XY, and movement of E2. So E1, E2 are standard vector 1, 0, and 0, 1, delta Y. And of course, it maps to UV to V1 and V2. So V1 is assumed to be the transformation of E1 vector by the differential of t, taking E1 delta t, and V2 is dt E2 delta y. So what's the differential? Differential is simply ux, uy, vx, vy. And I'm taking the multiple of E1, which is represented as 1, 0 column vector, delta x. And same thing, but here we have 0, 1 column vector. So let me give a space between here. So V1 is, when you take the matrix multiplication, you get this one multiply this one to get ux, and the second row, first column, to get vx times delta x. So you can imagine that V1 is ux, vx times delta x. And how about V2? The same thing, but you take, so vx, ux, vx is simply the first column of your differential. So when you multiply E2, you get the second column of differential, which is uy, vy times delta y. So it's uy, vy times delta y. That's your V2. So it's a small vector because delta x and delta y are multiplied. Because it's small, we can assume that this parallelogram bounded by V1, V2 is approximating the area of the section corresponding to this section. So if I say this is my u here, u, x, y, then the actual region that is corresponding to ux by the function t might not be actually the parallelogram. So maybe it's similar to this. So t of ux might be slightly off from the parallelogram. But since, as I said, vectors are small, so we're taking the small increment or small changes. It's all, you can imagine these are the almost same thing. So I can take the area of parallelogram bounded by V1 and V2 to approximate the area of our image. So area of the image of small region is approximated by area of parallelogram bounded by V1 and V2. So how do you get the parallelogram bounded by V1 and V2? What's the area? How do you get the area of two vector parallelogram of these two vectors? You simply take two vectors as column or row vectors of 2 by 2 matrix and compute the determinant. That's the area of parallelogram, or determinant, absolute value of determinant. So this is equal to the determinant of V1, V2, which is what? Since V1 and V2 are first column and second column of the differential, multiply to delta x and delta y. Let's see. This is ux, vx, delta x, delta y, and this one is uy, vy, delta x, delta x here, and delta y here. So you have the same thing multiply on the one column, so you can take them out, delta x here, and you also have the same thing multiplied on the second column, you can take them out when you compute the determinant, and you get uy and vx and uy and vx and vy. Okay, so again, so when you take the determinant, it could be negative, but it means that the order of your vector is, the orientation of vector is reversed. So since we are talking about the area, we need to take the absolute value. We don't care about the orientation reversing. So we take the absolute value here, and this is the Jacobian. The absolute value of Jacobian. And what is delta x and delta y? That's exactly the area of the image, area of uxy. So what does Jacobian mean? So even though it's an approximation, it's gonna be almost equal when you have a small delta x and delta y. So it says Jacobian is approximately equal to the area of the image of the small region over the area of the domain. So so now it's clear why we are multiplying the Jacobian. Since we are talking about changing the integral symbols here, when you take the integral over du dv, it has certain value. But when you map this area, small area, to xy plane, it changes the area. Right? You cannot use the same area inside of UV plane and take that as an area of that image, because image has different area. So how much do you have to multiply in order to get the same area? You need to multiply this much to the area you have in xy plane to get the same area. So that's the integrating factor. Integrating factor has different meanings. So anyways, factor that you need to multiply so that you get the same area of the integration. Okay, so the reason why I like this notation for Jacobian is that you can think of this as canceling out dx dy on the bottom and here. So you get the dy, the du dv as in the right place. So this way it's clear what kind of transformation you need to use to find the substitution. So let me give you an example here. So look at the integration first. I want to take the integration over xy region. So now you have to free your mind that it's not always xy to uv. You can change your direction of transformation. So now what I want is the integration over x and y over the xy region D. And this seems impossible because now I have this region, x and y region. Similar, so here, which one is this one? This is my region D. Okay, so I want to integrate this function over this triangular region. Well, maybe it's possible, but not easy. So I want to make it an easier way of integrating by taking a substitution. So instead of having this, okay, so I want to take a transformation which makes this integrand simpler. So let's take this way. So remember that picture. So what I want is I want to use the integration by substitution like this. So this is what we want. The right-hand side is what we want. And what we are trying to do is trying to change this integral into another integral by integrating Jacobian and then function in terms of uv over some other region u. So u is here inside of UV plane. Okay. So our function is exponential, is it y? Y over x plus y. So if I want to make it simpler, the problem that makes it harder to integrate is because x plus y is in the denominator. So if I just substitute entire thing into u, then and this thing to v, then it makes it a little bit simpler. So I'll take this as exponential v over u. But then let's look at the substitution. I substituted x plus y as u and y as v. That means I have a function from xy to uv that sends xy to x plus y, y. Right? But let's look at the let's look at the Jacobian or integration by substitution. We want this as Jacobian. So this means this is Jacobian of the transformation that sends uv to xy, right? Because xy is on the top, okay? But by substitution, what we found is xy is sent to uv. So therefore, this is what we want, but this is actually the inverse of what we need to plug into the integration by substitution. So we need to find the actual t by reversing this. So let's rewrite this in terms of x and y. So x is u minus v and y is simply v. Therefore, t is uv tending to u minus v. That's my xy. So let's find out what is u. So u is sent to d, where d is x from 0 to 1 and is it right? So yes, y is from 0 to 1 minus x. Okay. So I want to find which domain inside of UV plane that maps to this triangular region through the transformation T. Well, you don't have to do the try and error because we already have the inverse mapping and we know that this is one-to-one mapping. So what we need to do is simply take opposite 3 the vertex of the triangular region D, 0, 0, so that's D. And then if I take the inverse map of this, I only need to take, okay, so, but this is only because this T is a linear function, so I know that the line goes to line through the linear transformation, so all I need to do is just take the vertex and then see what are the vertices and then connect those vertices to get another region. So to get the u, let's see where does 1, 1 goes. So 1, 1, d again is in the xy plane. So these are x and y coordinate. So when x, y are 1 and 1, then I get 2, 2, 1, right? So it's 2, 1, so opposite. So that's u and v. So that's 2, 1 here. And 0, 0 goes to 0. And 1, 0, 1, 0 goes to 1. UD. Oh, sorry. Oh, D is not this one. Sorry, I made a mistake here. So D is not this one. D is this one, right? This is D. So the vertex is 0, 1. So where does 1, 0 go? 1, 0 goes to 1, 0. And where does 0, 1 go? 0, 1 goes to, yes, 1, 1 here. Okay, so that's my U. So this is the integrating domain for the new integration after I apply the integration by substitution. Okay, so let's go back to our formula here. I want to rewrite this. Okay, so what is this part? Simply substituting x and y by uv. So we already did. This is your f composite t in terms of uv. So we're gonna use this, and we already have u. And what is this part? Since we have t, let's compute this determinant of dt, which is determinant of 1 minus 1, 0, 1. So it's a linear function, so easy to compute. It's 1. So it's gonna vanish here. So it's 1 since it's 1. So simply it's an integration over u and v of this function over the region u. Looks like this. So let's rewrite this here. U exponential v u du dv. Now it's a matter of you can take the iterated integration or Fubini theorem to find this. So let's see. Let's start from u. So I'm gonna rewrite my u, the region u, in terms of following. So small u is range from u, while v is range from 0 to u. So I'm gonna integrate v first and then u next. So v range is 0 to u of exponential of uv, and then u range from 0 to 1. So that's 0, 1. And when you take the integration of these functions, let's see. U is considered as constant. So u times x of uv is your antiderivative, right? So that's for v from 0 to u du. And when you plug in u into the v, then you get u exp of 1. And when you plug in 0, you get just u, so du. So the rest of the calculation is easy, so I'll leave it to you. So that's how you get, you can compute the integral. So integration by substitution, it's a bit tricky. Okay, so let me see if I have another example here. Not really up here. All right, so let me give you an example so that you can exercise. I don't want to move too quickly here. So let's think about okay, so here's an example. So exponential minus x minus y dx dy, where d is, let's see, d is the region whose center is the origin and the radius is 1, circular region here. So I want to find out this integral. So of course, you cannot do it with the Provini theorem because there's no way, I mean, unless you want to find a numerical value to estimate this integral, if you want to find exact value, then there's no way you can do it because without doing any substitution, because you cannot get any antiderivative exponential function with the x squared inside. Okay, so cannot write the antiderivative in with known function. So our trick is to use the integration by substitution. You have to use the polar coordinate system. So you have to use this polar transformation here, this t. So I'll give you time to discuss about solving these questions, and then we'll move on then. Okay, well, let's do it together. Um, so here, don't try to memorize the rule of substitution. Um, so, well, so you have to understand what the symbols of the integration by substitution says. So what we want is we have this function or not function, so integral dx dy and we want to change it into some function in terms of r theta and something, maybe probably Jacobian, dr d theta. So we want to translate it into, translate the dx dy integral into dr d theta integral. So this function has to be the same function as this one by substitution. But what we want here is the Jacobian, which factors the difference of the area between xy plane and r theta plane. So what we want is dx dy on top and rs dr theta bottom, because then we can cancel out to get dx dy. So that's what we want here. But we already have a function to compute that Jacobian because tr theta is sent to xy. So this one is determinant of xr, x theta, yr, y theta. It's determinant of, so this is x and this is y. So this is cosine theta minus r sine theta and sine theta r cosine theta. So when you take the determinant by multiplying cross, then you get r. So r is positive in the polar coordinate, so you don't need to take the absolute value. So you get r in here. And what is fr theta? You simply substitute x and y. So it's minus r squared. So exponential minus r squared times r dr d theta. So we are taking the double integral, but it's easy to use it's better to use fluidity theorem to use the iterated integral. So we need to figure out what u is. So u is the domain of the transformation function whose image is the given region, which is the circular region. Since it's a polar coordinate, the transformation is polar coordinate, it's easy to think about what that is instead of writing or drawing things. But here is our d. So radius can up to 1. So if I say this is r, then radius can go up to 1. And the angle theta can be from 0 to 2 pi. So r is from 0 to 1. Theta is 0 to 2 pi, and these two r and theta are independent in order to comprise all the region inside the circle. So this is our u, the rectangular region. So you can simply take 0, 1, 0, 2 pi, whichever order you want, and integrating r, the theta first, the r. So since there is no theta, so these r, the function of r, is considered as constant when you take the iterated integral of the theta first. So we can take out this integral exponential of minus r squared r dr times the integral over 1 of theta. So it's 2 pi. 2 pi and then minus 1 over 2 x of minus r squared, where r from 0 to 1. Get the number. So typically when you have the symmetric expression of x and y inside of integrand, you want to try the polar transformation. And also you can do the similar thing on the three variable function. So I'll briefly explain the integration by substitution in triple integral and then see the example. So same idea. You want to change the integrating domain. Here it's a three-dimensional domain. So this is what we want. But we want to transform this into here. If the region R is given as xyz, inside of that xyz space, then I want to translate that R to the region V inside of UVW space, then transformation is T. I simply rewrite my function in terms of UWV, but the problem is when I translate the domain, then the volumes are different. So XYZ volume and UVW volume are differed by this amount. The reason, brief region, is that when you have a square region, when you have a cubic region inside of UV plane, you can map that cubic region into a region inside of XYZ space, and the region, the image of that region is approximated by parallelepiped bounded by three vectors, which corresponds to three standard orthogonal vectors, E1, E2, E3. So what are these three vectors that bounding parallelepiped? These are exactly the first column vector, second column vector, and third column vector. So as we mentioned before, the very first day of our class, when you have three-dimensional vector, three-dimensional vectors, and you take the columns or the rows of 3x3 matrix, the determinant is the absolute value of determinant is the volume of the parallelepiped. So this ratio, this Jacobian is approximately the ratio between the region of cubic region inside of UV plane to the region of parallelepiped bounded by the image of the vector. So that's why we have to multiply this Jacobian here. And let's look at this example. I'll do it together here. We have a region, the sphere region. So, and everything is symmetric. So you can thinking about using the spherical coordinate, spherical transformation. So I'll write it here. Our region is the sphere, and I want to compute square root 1 minus x squared, y squared, z squared, dx, dy, dz. So let's try to use okay, so r theta phi. I think I didn't never mention the spherical transformation. Did I? Do you know spherical transformation? So the spherical transformation or spherical coordinate is identifying point in the xyz coordinate in space by taking the sphere, and you have a radius of a sphere. So you always can identify one sphere where the point lies on, that's your R, and you have the angle from the z-axis, which is phi, and then when you take the projection here, and this is x and this is y, you get the angle between the projection line and the positive axis of x, that's phi. So spherical coordinate says when you have r theta phi, then you get x and y z coordinate. So first of all, what's the z coordinate? Z coordinate is cosine theta of r. So r cosine theta. And x coordinate is when you project it onto xy plane, the radius is r sine theta. And the angle between the positive x-axis gives you the angle determining the xy coordinate. So it's cosine phi and sine phi. So it's a long computation to compute the Jacobian, but I'll just give you the result. So when you take the Jacobian of these spherical coordinate, it's a determinant of 3x3 matrix. It's r squared sine theta. Okay. So I'm going to use this to rewrite this integral. So let's say V is the region corresponds to the region R, and inside of the r theta phi region. And what's the what's the integrand? It becomes 1 minus r squared, simple. And then you need to multiply Jacobian because I want to translate my xyz integral into dr d theta d phi integral. That's why I get this dx dy dz. So anyway, so I want to keep this. And what is Jacobian? It's r squared sine theta. Again, r is positive, and of course, it's squared, so it's always positive. And sine theta is always positive because theta can range from 0 to pi, from north to south, and sine theta in that case always positive. So I don't need the absolute value sine, and that becomes r squared sine theta 1 minus r squared dr d theta d phi. Okay, so what is v? If we want to make up all the inside of the sphere of radius 1, my v should be the range of, okay, so for r theta phi, that goes inside of all the sphere, of unit sphere. So r must be from 0 to 1. And theta, which determines the height, is range from 0 to pi. And phi is from 0 to 2 pi. So it's simply the cube of r theta phi region. 0, so let me take 0, 1, theta 0, pi, and 0, 2 pi. So you can compute this because now without the Jacobian, if you have this square root of 1 minus r squared, oh, you can do it by substitution, but still, if you have r squared, you also can do it. And the phi, there's no phi, so it's just this constant, and there's a theta, sine theta, so when you integrate over 0 to pi, it's 2, so you can get the answer quite easily. So, if you want to get used to this integration by substitution, you need lots of practice. So there are many tricky problems, but I don't like doing those kind of problems. That's why I'm not lecturing in the conventional way, because what you need, again, to wrap up, what you need is to understand of the principle lying inside of the integration by substitution, which means what's the meaning of Jacobian. Okay, the Jacobian, for in the two-dimensional case or three-dimensional case, it's the ratio between two small volumes correspond to each other by the one-to-one mapping of transformation. Then it is used in the integration by substitution to make up the change of the domain. Because what you are doing in the integration is multiplying your value of function to the area of the region or volume of that region. So since you change the domain, change the coordinate system, you change the volume. So you have to make up the change by multiplying the Jacobian. That's what we are doing in the integration by substitution. So again, well, integration by substitution usually are useful when you try to find the exact value of integration. But as I said, the point of doing the integration is getting the value. It doesn't matter whether you get the exact value or approximate value. As long as you get the number, then it's fine. So, and well, it's worth knowing what the integration by substitution is, especially when you have to use the transformation, polar transformation or sphere transformation, because it appears many times in the theoretical background of physics and also some mechanics. But you have to, as long as you understand the principle, you have no problem following that theory or theory behind. All right, so there is a stuff that I had put on the slide at the end. It's about the improper integral. I'm gonna just let you to read it and gamma, and also about the gamma and beta function. And we'll resume next time about the Cost-Crossing formula, which is our step 6 project or 7th project. All right, so if you have any question, let me know, or see you on Wednesday.